Okay, so this is a decision tree that I've sketched out for the three tests that we are employing for exam 3. So I'm just going to walk you through this real quick, and I'll post this, and you can use it on the exam too, since it's open note. So if we're dealing with a question that's related to differences between one or two averages and sigma is unknown. So really it's kind of a difference between two averages, but I put between one or two because it's in one of the cases you're dealing with one sample mean, and you're trying to determine if if that provides evidence that one average under the true population mean is different from that, or less than or greater than. So that's the one sample t-test scenario. So it's really technically two averages. You're kind of comparing, it's kind of like you're comparing this sample mean to see if it's actually from a different population than the null hypothesis. So you're kind of comparing those two, but in reality it's really just, but you're really just kind of dealing with one average. You don't have two averages that you've computed. So just hopefully that makes it less confusing instead of more confusing. But I think you've had enough practice that you can recognize when we're dealing with questions like this, where we're dealing with differences in averages, okay? As opposed to relationships where we do something like a correlation or a regression, or a multiple regression or something like that, okay? And then the other key part of this is that sigma is unknown, okay? So we've answered questions similar to the ones we've been doing with t-tests, but we were using z-tests, okay? So if sigma is known, you can use the z-test formula. That's got sigma in it, whereas t-test formulas just have s, the sample standard deviation. So you try and estimate sigma using s. So if sigma is known, then you'll use the z formula. Okay, so let's say we've established we're asking a question related to differences and sigma is unknown. Then we're going to use a t-test. Now, another reason, just real quick, why I put one or two averages is we're going to be looking next to the ANOVAs when we're dealing with more than two averages. And in that case, you wouldn't actually use a t-test, you'd use an ANOVA, but we'll get to that later. Okay, so right now we're using a t-test, and we've talked about 4 different kinds. So use a t-test. Let me just skip here. We want to know, do we open this drawer, do we open this one, or this one? One sample matched pairs or a 2-sample t-test. You know, we have 2 different flavors of that. Okay, so the 1-sample t-test is kind of the easiest decision to make. If there's just one sample, then you use a 1-sample t-test. And pretty much that just looks like you've got one column of data, and so you're gonna use the 1-sample t-test. Now, Excel is kind of stinky because it does not have a function for the 1-sample t-test. So you have to play some tricks in Excel in order to do that. And you can. You just have to use the matched pairs t-test function. And that's where you're going to create a dummy variable, usually in the column just right next to the variable of interest. And the number that you put in for that dummy variable is going to be equal to the hypothesized mean under the null. You can see, you can reference all of that in the help doc for what that dummy variable actually looks like. But usually it's going to be a column of zeros. Okay, usually the null hypothesis in a 1-sample t-test is that mu naught is equal to 0. Okay, or that mu is equal to 0. Okay, so there could be other situations in which it would be something else, like if there's a population mean that's claimed, that's out there, or that's known, and you have some data and you want to see if it's actually different from that, but you don't know sigma. Okay, so usually that's kind of rare because if you know mu, you'll often know sigma, but there are cases in which you know mu but you don't know sigma. And sometimes you might have some idea about mu that's meaningful in some way, and that's what you kind of say is this is my null hypothesis. I want to see if there's evidence to reject it. Okay, but you put whatever that value is for mu. If usually it's going to be 0, but sometimes it'll be 5 or 10 or some other number. Okay, and you'll put that in your dummy variable column. Okay, and then you'll perform the match pairs t-test, and you'll select one column for the one variable, and then you'll select the dummy variable for the other one. The hypothesized mean difference, even though you're dealing with a different, sometimes you might be dealing with a different mu, the hypothesized mean difference between those two is still almost always going to be 0. There may be special cases in which it's not, where you hypothesize there's some meaningful difference that you want to test between those two means, but usually the hypothesized mean difference is going to remain 0. Okay, so match pairs t-test, we already kind of addressed this a little bit, but how do you know when you should do a match pairs t-test? And really, the decision comes down to this is kind of all on its own because you've just got the one sample, and here you've got 2 samples. Okay, so you need to decide, are these paired? Is this paired data? Are these matched pairs, or are they independent from each other? Okay, and the way that I describe making this decision is if you were to highlight just one column of your data, so you've got those 2 columns, if you were to highlight just one and then say sort it from smallest to largest. Okay, now usually you don't want to do that in Excel, right? You want to keep things paired up, and so if that is the case, if you were to do that and you're like, oh no, I just shuffled up my data, now I don't know which numbers go with which ones, then you're dealing with paired data. Okay, if doing that would cause you to freak out, then you're dealing with paired data. Okay, so some examples would be before and after measurements. Maybe here's the weight before treatment and here's the weight after treatment. But those 2 numbers in those 2 columns, each pair is associated still with just one person. There was one person who had their weight measured before and after. There were multiple measurements, 2 measurements on each individual. Okay. Or it could be, population in 2016 and then population in 2017, 2 measurements taken on each state. Okay. Now, there are other kinds of paired data than just 2 measurements on the same individual. Sometimes you've got like identical twins or whatever, and those 2 individuals, even though they're only getting measured once, you still want to keep them paired up with each other. You want to keep the twins together in your data, or couples like husband and wife, things like that. Okay. So if you have paired data, then go ahead and do the matched pairs t-test. Okay, now if you've got 2 samples and they're independent, meaning you could shuffle one up and it wouldn't matter. You'll still get the it doesn't freak you out. Like if you got, here's the South and here's the West, or here is students from Dixie State and here's students from SUU. Then you could shuffle up those numbers in one of those columns and it wouldn't matter. And sometimes you'll even another way to tell, another pretty good giveaway is if you've got unequal sample sizes. Okay, so if you've got unequal sample sizes, then you pretty much have to have 2 independent samples unless you have missing data or something like that. But we won't get into that. But if you have 10 individuals in one and 12 in the other, that's probably not paired data. So that's a pretty good giveaway. So the 2 sample t-test, that's very commonly employed. There are actually 2 flavors to it though. Okay, one where we have equal variance assumed and one where we have unequal variance assumed, or homogeneity of variance assumed for the equal, or heterogeneity of variance assumed for the unequal. That's another term that you'll see in Excel. Okay, so and these are the criteria that you use if the sample sizes are approximately equal. And it'll be obvious if it's not, and the variances are approximately equal, where one is no more than 4 times the other, then you use the equal variance assumed. And if they're not approximately equal, then you'll use the 2 sample t-test with unequal variance assumed. Okay, so that tells you which drawer to open. Now, things that you're going to need to report for a t-test, if you're writing a paper, are p-value, degrees of freedom, and the t-statistic. Okay. Now, the t-statistic and the degrees of freedom, those you can get from your output. And the main question that you need to answer in terms of making a decision based on the question that you see in an exam or whatever is, do you use the two-tailed p-value or the one-tailed p-value? Because the output is going to give you both. And also the t.test function, you can select, do I do a one-tailed or do I do a two-tailed? Okay, so this is, depending on how you do it, this is a question that you might make before you do any analysis. Well, I mean, you should do it before you do any analysis, but you might need to make this decision before you even run a function at all. Okay, so look at the question. If the question is asking if the averages are different, like is the height of Dixie State students significantly different from the height of students at SUU, then that would be, there's not a direction associated with that. It's kind of both directions. So you'd use a two-tailed p-value in that case. You're just trying to test, is this different? Is it not equal to, is one average not equal to the other, or is this average not equal to the hypothesized mean under the null hypothesis? Okay, and then if it asks either less than or greater than, and there might be different words, it might be like higher or lower, less, greater, more, an increase or a decrease, things like that. Something suggesting a direction, just one direction, either getting higher or lower, then you would use the one-tailed p-value. Okay. Now, if you got the one-tailed p-value and you realized, oh no, I actually needed the two-tailed, how do you get to the two-tailed? You just double this, times this by 2. Don't times it by itself, just times it by 2, and that'll take you to the two-tailed p-value. Okay, so hopefully that gives you a good overview of how to walk through these decisions for which t-test to employ. And that's all.